All right, so in this last presentation, I want to talk about a secret code of creation. Wouldn't that be neat if there was a secret code built into some aspect of creation? There was the movie a few years ago. What was it? National Treasure, right? Where Nicolas Cage found a secret code on the back of the Declaration of Independence, and that indicated that there were some really intelligent people that built that code in there. Codes always indicate intelligence, and so what would happen if we found a code built into numbers? That would be awesome, wouldn't it? Because it would imply that there's an intelligence behind numbers. We don't think of God creating numbers. We think of God creating physical things, planets and stars and animals and so on. But God is also sovereign over the abstract world of mathematics. And so God's mind is responsible for numbers just as much as it's responsible for the physical creation. What would happen then if we found a secret code built into numbers? Numbers 1, 2, 3, 4. What if there was a pattern built in there? Well, there is. There is. And this was discovered in the 1980s, and it is mind-blowing. And I just want to share it with you because it's cool, and it has no secular explanation for it. You cannot make sense of this from any perspective other than the Christian worldview. And so it is just very powerful confirmation of the Christian worldview. Very awesome. And I have to start by saying that when I was young, and my mother would prepare these wonderful meals. She's a very good cook, and I would enjoy that. But every now and then she would make something I didn't like broccoli. Ugh. But the rule was you had to eat everything on your plate before you could be excused and do what you wanted to do. And so in rare moments of maturity, I would occasionally eat the broccoli first, kind of get that out of the way, and then I could enjoy the rest of my meal. Does that make sense? Well, in the same spirit, we're going to have to do a little broccoli first, but stay with me because it's going to get really cool, and you're not going to enjoy the rest of the meal if you don't go through the broccoli. That's just the way it works. So we're going to have to do a little bit of definitional stuff with mathematics here, and this is all high school stuff. It's not that difficult, but stay with me because it's going to get really good really fast. We're going to talk about sets. A set in mathematics is just exactly what you think it is. It's a collection of numbers that have a common property. And that property could be anything. You can define your own sets. And in most sets, some numbers are included in the set, and then other numbers are excluded from the set. That's pretty easy. So, for example, we could consider the set of even numbers, the set of even numbers. Well, the numbers that would belong to that set would be all those ones, those numbers that are, when you divide them by 2, you get an integer. We understand that. So that's the set of even numbers. And so those numbers would be included. Those numbers at the bottom would be excluded, right? So that's pretty easy. We could consider the set of negative numbers. Now, this is a different set, and so different numbers will belong to it. The set of negative numbers would include numbers like -3, -0.5, and so on, and then it would exclude all those other numbers, right? So that's pretty easy. Now, those two sets are very simple. They're very easy. You can tell just by looking at the number whether or not it belongs to the set, right? You look at the set of negative numbers. Does it have a little minus sign in front of it? Then it belongs. Easy. Some sets are defined in a way that's a little more complicated, where you can't tell just by looking at the number whether or not it belongs. You're going to have to do a little bit of work to figure it out. And so what we're going to talk about is what's called the Mandelbrot set. And the Mandelbrot set is defined according to this simple little formula, and it is very simple, and I'll walk you through it. But it's defined, the Mandelbrot set is defined as all the numbers C. C is a candidate for the Mandelbrot set. We want to see if the number C does or does not belong to the Mandelbrot set. It's the set of all numbers for which the sequence Z, which is another number, remains small according to this little formula. And I know that sounds complicated, but I'll step you through it, and you can see how it's actually very easy. So basically Z, and the fact that Z has a little n under it means that there's lots of Z's. There's Z1, there's Z2, Z3, and so on. There's a sequence of Z. And if that sequence of Z stays small, like 0, 0, 0, 0, 0, that would stay small, wouldn't it? Then the number C does belong to the Mandelbrot set. If, on the other hand, that sequence of Z gets very big, if it goes 1, 2, 1,000, a million, infinity, then in fact C is not part of the Mandelbrot set. You got that? Let's run through a couple of examples just so you can see it. So we're going to ask, is the number 1 part of the Mandelbrot set? So our candidate that's potentially part of the Mandelbrot set is the number 1. So C equals 1. We plug that into our little formula. So we have z squared plus 1, that's the number we're evaluating, is zn plus 1. Zn plus 1 means that's the next value of z. And so what we're going now the first value of z always starts as 0. That's just part of the definition there. And so we're going to start with 0 squared plus 1. That's pretty easy. 0 squared plus 1 is 1. Yeah, that's right. 0 squared is 0 plus 1 is 1, right? You're all Common Core educated, aren't you? Okay. So that's the new value of z. Okay, so we're going to record that on our list. So z started as 0, now it's 1. And then what we're going to do is put that back in. That's the next value of z. So we're going to put that back in. So now we got 1 squared, which is 1, plus 1 is 2. All right, very good. We're going to put that back in. So now we have 2 squared, which is 4, plus 1 is 5. Okay, put that back in. 5 squared, 5 times itself is 25, plus 1 is 26. Put that back in. 26 squared plus 1, it's a big number. Okay, and so on and so forth. Now, is the sequence of z staying small? No, it's getting big, isn't it? So is the number 1 part of the Mandelbrot set? The answer is no, because the Mandelbrot set requires the sequence of z to stay small. That sequence did not stay small. It got really big. And you can see it's just going to get bigger and bigger, isn't it? It's just going to get bigger and bigger. So the number 1 is not part of the Mandelbrot set. Had to do a little bit of work, but we got there, right? Let's try another one. Is the number -1 part of the Mandelbrot set? So now we're going to put c equals -1. We're going to put that into our formula. So now we're going to have z squared minus 1 is the new value of z. Z always starts as 0. So we have 0 squared minus 1 is -1, right? We're going to put that back in. Now -1 squared, -1 times itself is +1. Minus 1 is 0. Well, that's interesting. Put that back in. This looks familiar, doesn't it? 0 squared, what's -1 again, isn't it? Put that back in. -1. Oh, that's interesting. It just kind of oscillates, doesn't it? 0, -1, 0, -1, 0, -1. Is the sequence of z staying small? Yes, it is. You can see it's never going to deviate from 0 or -1. It's staying small. So is the number -1 part of the Mandelbrot set? Yes, it is. Okay, you got that? So it's a little tedious, but it's not intellectually difficult. You just have to run it through the formula a few times. And I won't do any more of that because you get the idea, and it is tedious. So there's one more complication, and then we'll get to the really cool stuff. Okay, the other complication is that the Mandelbrot set also includes the so-called complex and imaginary numbers. And boy, I hate that name because imaginary makes you think like it doesn't exist. But an imaginary number, they do exist, but they are the square root of a negative. So when you multiply an imaginary number times itself, you get a negative number. And the primary imaginary number is abbreviated by a lowercase I. So I squared equals -1. And that's challenging to us, isn't it? Because how can you multiply something by itself and get a negative? I mean, imaginary numbers are not positive because a positive number times a positive number is a positive number. And yet imaginary numbers are not negative because a negative number times a negative number is a positive number, right? And yet they're not 0 because 0 squared is 0. So it bothers people. How can you have a number that's not positive, it's not negative, and it's not 0, and yet they do exist? Yes, they do. I hate the name. They're imaginary. It makes it sound like they're not, they don't exist. And to add insult to injury, numbers that are not imaginary are called real. It's just a name, though. It's just a name. So, but how do we make sense of a number that when you multiply it by itself, you get a negative? A number that's not positive, not negative, not 0. Well, I have to point out that this may be counterintuitive because our intuition is based on experience. And most people don't have a lot of experience with the so-called imaginary numbers. It's kind of like when you were a little kid and you were first introduced to negative numbers. That might have bothered you, right? I mean, you come to understand one apple, 2 apple, 3 apple. How can you have less than 0 apples? That doesn't make sense. How can you have less than nothing? It doesn't make sense when you're a little kid because you don't have any experience in that. But you get a little bit older, you get a bank account, suddenly negative numbers make a lot of sense. Yes, I can have less than nothing. So, well, imaginary numbers are the same way. You can have numbers that are not positive, not negative, not 0. It's just most adults don't have a lot of experience with that, so it's kind of bothersome to us. How could we think about these? Well, here's one way you could think about it. Consider a number line. So the numbers that are to the right of 0, those we would call positive. The numbers that are to the left of 0, we would call negative. Where are you going to put an imaginary number? It can't be to the right of 0 because that's positive. It can't be to the left of 0 because that's negative. And it can't be at 0 because that's 0. You can think of an imaginary number as being off axis like that. Yeah, that makes sense because it's not to the right of 0. It's not positive. It's not to the left of 0. It's not negative. And yet it's not at 0. It's along a different axis. And so you can think of the imaginary numbers as being sort of perpendicular to the real numbers. And by multiplying I by any of the real numbers, you can end up with other imaginary numbers. And they obey all the ordinary rules of algebra. You just need to remember that whenever you have I squared, that's equal to -1. You can also have numbers that are off axis. You can have a number that has a real component and an imaginary component. And those are called complex numbers because they have two parts, a real part and an imaginary part. And usually we represent the real part as being along the x-axis, and the imaginary part as being along the y-axis. And this is really neat. This is called an Argand plane. And it's neat because I can represent any point on a plane with one number. It's got two parts, which is why I can represent it on a plane, with the real part indicating the x-axis, the imaginary part indicating the y-axis. Now, what I pointed out is that the Mandelbrot set also includes these imaginary and complex numbers, not just the real numbers. And we checked two of them. We checked 1 and we checked -1. We found that 1 does not belong to the Mandelbrot set, but -1 does. What if we check the imaginary numbers and the complex numbers? Well, you'd find some of them belong, some of them don't. But that's tedious to go through and check each one, so we'll let the computer do it. Computers don't mind doing tedious things. And what we'll do is we'll make a map of the Mandelbrot set, because I want to see if there's a pattern here. Is there any pattern to those numbers that do or do not belong to the Mandelbrot set? And so what we'll do is we'll take the points that do belong, and we'll color those black. And we checked -1. We found that it did belong. I've checked 0. It plugs 0 and it just stays 0, 0, 0. The sequence of z stays 0, so it belongs as well. And so we'll color those black. And had we checked these other points, we would find that these points all belong to the Mandelbrot set. So we'll color them black. I'm just picking points at random and find that those points do belong. And then points that don't belong to the Mandelbrot set, we'll give them a color, like red, for example. It wouldn't have to be red. I can pick any color. We found that the number 1, does not belong to the Mandelbrot set, so it gets colored red. Okay? And had we checked these other points, we would find that these do not belong to the Mandelbrot set, and so they get colored red. And so you see what happens is we're making a map of which points belong to this little formula, z squared plus c. When you run it through that, when you run z through there and you see z stays small, you color it black. Z gets big, you color it red. Easy. And what happens as you check more and more points is that a shape starts to emerge, and the shape that emerges is fascinating. And it's not something that anyone expected. So let me just cut to the chase and show you what happens when you map out the Mandelbrot set. This is the shape that you get. And it's really a strange kind of shape. And again, I'll explain. Those points that are black are points that do belong to the Mandelbrot set. Those points that are colored do not. And I even shaded it. So points that where the sequence of z gets really big really fast, I made those kind of a dark red color. And points where z got big, but it did so slowly, I colored those a lighter color, like light yellow. And so you can think of the bright points as being very close to the Mandelbrot set, but they're not quite on it. Okay? And then points that are black do belong to the Mandelbrot set. The sequence of z stays bound. I think it never exceeds a value of 2. Okay? So now we just look at the map and we can tell which points belong to the Mandelbrot set. You can see that 0 does. You can see that that -1/2, there's -1/2, that belongs. Half I does belong. I does belong technically. There's a little black spot there, and so on and so forth. So we've had the computer run it through, and we don't have to go through that little formula ourselves anymore because that's tedious. The computer's done the work for us. And it's interesting that the shape that emerges here. So you have the large structure here. You have a perfect circle that's centered exactly on -1 and has a radius of exactly 1/4. The last point is -2. There's a spike that comes out here that's covered up by the graph that I'll show you in a minute. There's a cusp here. A really interesting shape. Now I'm going to go ahead and remove the axes lines because what's interesting is not so much the fact that these points belong to the Mandelbrot set as the shape itself. Nobody was expecting that when you made a map of points of the Mandelbrot in the Argand plane that you would end up with such an interesting shape. And it has all kinds of interesting properties that we'll explore here. So notice the basic structure of it. You have this sort of heart-like structure here. This is called a cardioid. Now, a cardioid is what happens when you take a circle and you roll it around another circle of equal size, keeping your pencil affixed to one spot on the circle. Let me show you this. So here's a cardioid. You see, I'm keeping my pencil on one spot on the circle. That's the shape that it makes. And that is the exact shape of the primary lobe of the Mandelbrot set there. Isn't that interesting? And then all the other geometric shapes we see are either perfect circles, and they are perfect circles. They're exact. And they have circles growing off of them and circles growing off of them. And then we have these little tendrils that grow off to the side, like little branches that branch off, including a straight one here, a spike on the end, and a little bump on that, and so on. And what we find, all we're going to do now is just explore this shape that nobody was expecting, because it turns out to be really interesting. And it's got some interesting properties to it as well. We can zoom in on various portions of the shape, because the computer's already done the work for us. It's already made this map, and we can zoom in on it a little bit. We find, for example, that when we explore the upper portion of the cardioid, you can see these circles that you have there. And on top of them are growing off these little trees with branches. And you notice the first one here branches, it's got 3 total. It's got 2 and then a stem. So it branches off into 3, right? Now the next one down, on the next biggest bump, it's 1, if you count them, 1, 2, 3, 4, it's got 5. And the next one down is 7. And the next one down is 9, 11, 13, 15, 17, and so on. So each one gains 2 extra tendrils. So the Mandelbrot somehow understands odd numbers. Even though there was nothing in the equation that had to do with odd numbers, right? Somehow it knows how to count by the odd numbers all the way down to infinity, odd infinity, whatever that means. So interesting, isn't it? And on the other side, you have the odds and the evens. 3, that branches into 4, 5, 6, 7, 8, 9, so on. So the Mandelbrot set somehow knows how to count, which is kind of interesting. I guess it's not surprising that it has mathematical properties. It is, after all, a mathematical graph. But it's surprising that it has the particular properties that it has. Why would these tendrils branch off and have the properties that they have? It's quite fascinating. And what even really blew my mind was when I started counting the tendrils in between these 2 lumps. So this guy right here, which is in between this one and that one, right? He's the next biggest one in between the 2. Because this one has 3 tendrils and that one has 5. And you add 3 and 5 and you get 8. And lo and behold, that's exactly how many this one has. That's kind of interesting. Is that true of all of them? Yes, it is. Each one it's in between the 2 adds the number of tendrils between those 2. Every one of them. Every one of them. And it even works with the ones in between those 2. So if you took 8 and 5, lo and behold, that one will have 13, undoubtedly. So not only does the Mandelbrot set know how to count, it somehow knows how to add. It's kind of wild. Nobody was expecting this. Where is this coming from? How can we make sense of this shape? Well, we'll talk more about that later on. I just wanted to point out it's got these weird properties to it that nobody was expecting. Because all we're doing is making a map of what points belong to z squared plus c. That's it. And the map turns out to be wild. One of the most interesting aspects, though, of this map, well, the first instance of it occurs with this little spike out here. You might notice this spike coming out there, and it's black, so that tells you those points do belong to the Mandelbrot set. But then it's got a little bump on the end of it here, and I thought, well, what is that bump doing there? Let's zoom in on it and see what it looks like. We zoom in on that, we find that that's interesting. It's another Mandelbrot set, isn't it? And it's almost identical to the original. You have the cardioid shape here, you have the circles growing on top of circles, and so on. The only difference is it's got extra spikes growing off of it. You see these extra little spikes here? Those weren't on the original. It's kind of interesting because we zoomed in on a spike, and the baby version has extra spikes. Kind of interesting, like it inherits the property of the parent that it grows off of. And so, and I looked at that and I thought, well, that's interesting. That's got a little spike there too, and it's got a little bump on it. Now, what could that possibly be? And we zoom in on that, and it's another one. That's interesting. And they look at that. And of course, it's got extra spikes even because we zoomed in on a spike of a spike, and it's got extra spikes. And of course, it's got a little bump on it. What could that possibly be? And of course, you can do this literally forever. There are an infinite number of baby versions built into the original. Isn't that fascinating? And if we think about this, and I know I'm kind of being a little bit anticlimactic here, but how do we make sense of this? Well, in the Christian worldview, mathematics is the way God thinks about numbers. And so when we look at shapes like this, it's giving us a window into the way God thinks. Not that we can fully understand how God thinks. He's infinite, but nonetheless, we see aspects of infinity built into math because we're exploring something about the way God thinks. Pretty neat. And you could literally do that forever. But just look how small that baby is compared to the original. Pretty amazing. And any shape that's like that when you zoom in on it has a smaller version of itself built into it, is called a fractal. So the Mandelbrot set is one example of a fractal. There are other ones that we'll explore later on. It's not just the overall shape that repeats either. You can zoom in on a section of the Mandelbrot, and you'll find that no matter how much you zoom in on it, it looks kind of similar. And so, for example, if we zoom in on one of these tendrils that grows off here, you can see how they kind of spiral around. It's stunningly beautiful, at least I think it is. But as we zoom in on that, you think, well, it's going to end, right? Eventually it'll get down and it'll be nice and smooth, but it just doesn't. The more you zoom in, it just continues to branch off and branch off and branch into branches and branch into branches of branches and so on. And again, you can zoom on it literally forever, and it just keeps going and going and going, giving you a little window into the mind of God, not only his infinitude, but his beauty and how that's been built into creation. One of the interesting areas that I wanted to explore in this shape, and it's kind of fun to explore an aspect of God's creation that's non-physical, right? Because you understand, this shape doesn't exist. This shape isn't made of atoms. This is built into math, which is conceptual. It's not like you can point a telescope anywhere and see this shape. You say, well, I see it on the computer screen. Well, that's just a representation of it. The computer has graphed a finite range of this infinite shape. But the shape itself is interesting, and you could spend a lifetime exploring it because it is infinite. So let's just pick a few areas here. One area that's of particular interest is the area between the cardioid and what's called the main disc here. So the cardioid and the main disc, this valley right here, which is called the Valley of the Seahorses, or Seahorse Valley. We zoom in on that, and you can see what happens is on the right, it starts to look like seahorses. They're upside down, but you see that? What's happened is, remember those tendrils, how they go 3, 5, 7, 9? They keep increasing. After a while, there's so many of them, they start to spiral around each other, and you form these incredibly intricate sort of cobweb shapes. Now, again, I'll remind you that points that are black are points that do belong to the Mandelbrot set. The points that are colored do not, and the points that are brightly colored are very close to being on the Mandelbrot set. Now, the colors are arbitrary. I can make them whatever I want. And so every now and then we'll change them just to keep things a little bit interesting. But anyway, let's zoom in on some of these seahorses and see what they look like. And you can see it's amazingly beautiful. And who would have imagined that when you run numbers through that little formula, z squared plus c, this is the shape that you get? Nobody was expecting that. It's wild. And mathematicians were puzzled initially. They thought maybe this was an artifact of the way the computer's plotting it, but it's not. I mean, you could plot these points by hand. It would take forever, but you could do it. This is what you get. It's not the computer that's making this. The computer's just revealing it quickly. Now, because these points are bright, that tells you they're very close to being on the Mandelbrot set. It doesn't look like it, right? Because it looks like, well, the nearest black spots are over here. It doesn't look like there's anything there. But the fact that they're bright tells you they are very close to it. It's just what's happened is there's a very thin black thread of points that do belong on the Mandelbrot set that winds around very, very rapidly around itself. And it's just so small that it's smaller than a pixel, and the computer doesn't actually graph it. So you can imagine a very thin black thread weaving around and wiggling around like that and making this incredibly complex shape that you see here. And stunningly beautiful, I think. So let's zoom in on this seahorse. We'll zoom in on the central hub there. Isn't that neat? And I've found from experience that you can zoom in on the center of that hub and until your heart's content, and nothing changes. It goes on forever. And again, a little window into the mind of God. So I thought, okay, we'll go off axis then, because I don't want to just sit forever and zoom in on that. I might hypnotize myself or something, I don't know. But we'll go off axis and find out what these strands, because it looks kind of like a spider web, doesn't it? In the sense that you have a central hub and then you have these strands that spin away from it. So what happens if we look at one of the strands of the spider web? What are they made of? And so we'll zoom in on one of those, and we'll find that they're made of more spider webs. Smaller spider webs. Interesting. And a few spirals, like the spiral of the tail of the seahorse. You get a few of those. So isn't that lovely? And we'll zoom in on one of these shapes here. Let's zoom in on these. So here you find sort of two hubs of a spider web, one here and one there. and they kind of branch out. And in the middle, you have 4. 1, 2, 3, 4. And as we zoom in, it'll go to 8, 16, 32, 64. It multiplies by 2. So the Mandelbrot set knows how to add. It knows how to multiply as well. It knows the powers of 2. And as we zoom in on that central hub there, again, it goes from 2 to 4 to 8. So in the middle is another little baby Mandelbrot set. How about that? So there you see the 8, and there's the 16, and there's the 32 and 64, and so on. And then there's a little baby right in the middle. Almost identical to the parent, except it's got extra stuff growing off to the side. We zoomed in on a spider web, and so it's got all these spider webs growing off of it. And it's stunningly beautiful. And you'll notice it has a little bump over there too. Yes, it's got a baby version as well, just like the original did. So isn't that amazing? And look how small this shape is compared to the original when we zoom back out. It's just a tiny little section of a spider web that's growing in the valley of the Mandelbrot set there. Well, let's go back to the Valley of the Seahorses. The Valley of the Seahorses is on the right side. Now on the left, we have what's called the Valley of the Double Spirals. And mathematicians like to give fun names to these things. So the Double Spiral Valley over here, we'll zoom in on one of these and you can see why. We have a spiral. I really love this area of the Mandelbrot set. This is really pretty because it reminds me of spiral galaxies, which God also made. God is sovereign over math, is also sovereign over astronomy. And so we'd expect to find some of the same shapes there. This is a double spiral. What do I mean by double spiral? I mean there are 2 independent strands that wrap around each other. This strand right here, if you follow it around, wraps in like that, right? That's different from this strand. This strand is different, isn't it? Because it wraps around here, you can see that one's in between. So this and this are the same, that and that are the same. So 2 independent strands that wrap around each other. Some of the spirals in the Mandelbrot are doubles, some are single. This is a double. And it's incredibly beautiful. And so I thought, well, again, let's zoom in on it and find out what it's made of. And you find that it's more double spirals of unbelievable beauty. And again, keep in mind what's happening here. The black points at this, the black points that do belong to the Mandelbrot set are so small at this point. There's such a thin thread, you can't see very many of them. There's a few, a little black plate. You can see a little black spot there and one there, and a few. But mostly it's such a thin thread that's just weaving around and making this beautiful, intricate shape. And one of the structures here too that I think is really pretty, I call them bow ties. It looks like that little structure right there. It's like a little bow tie. It's got the two double spirals that intersect in the middle. And we find when we zoom in on one of these bow ties, it goes from 2, then you have 4 there, and 8, and 16, and 32, all the powers of 2, all the way into the middle. You're not surprised this time. It's another little baby Mandelbrot set there in the middle. And isn't that lovely? And it's rotated around too, you notice. Because on the main set, the cardioid's on the right, so it's been flipped around because we zoomed in on a spiral, and so it got rotated around. And growing off to the side are all kinds of these beautiful double spirals. Isn't that pretty? Who's responsible for that shape? Well, no human being made that, right? This is just what happens when you plug numbers into that little formula. And so you'd have to, well, who's responsible for numbers? Well, the answer is God's responsible for numbers. And so this is literally artwork of God. It really is. No human being sat down and decided to create this shape and that it should have these beautiful structures off. I haven't seen human artwork that compares, really. And certainly human artwork is not infinite either. This you could continue to zoom in. You could spend your entire life studying this shape and you've not even scratched the surface because it is infinite. And you might even notice that little baby right there. Yep, you could zoom in on that too. It's got its own Valley of the Seahorses and Valley of the Double Spirals. And you could zoom in on those. And they get more intricate and complex. The more you zoom in, the more intricate and beautiful it gets. Very unlike man-made machines. Man-made machines, the more you zoom in, the simpler they get. Right? Because eventually you get down to the point where we can't even construct it anymore. But this gets more complex as you zoom in. Interesting. Another valley that's interesting to explore is the one over here on the right of the cardioid. And they call this one the Valley of the Elephants. You'll see why when we zoom in. It's the only symmetric valley on the Mandelbrot where you have the same above and below. It's like a mirror image of itself. And you can see it looks like a bunch of elephants, one after the other. Isn't that interesting? Where they got the trunk that kind of curls up. Isn't that fascinating? And then on the top, they're hanging from the ceiling. So there you go. So a bunch of elephants. We'll zoom in on the lower stack here just so you can see a couple of these in detail. And you can see there's each one has its own little circle that it's growing off of. So it reminded me of like a circus elephant where they're balancing on a ball or something like that. And there's an infinite number of them. They get smaller and their trunk gets curlier the more you zoom in. But there's an infinite number of these elephants going into Elephant Valley. They just get smaller and smaller and smaller. So what happens if you zoom in on the trunk of one of these elephants? You have a single spiral. So this is a single strand, right? Because this strand, as it wraps around, it's the same as, those are the same. Those are all the same strand. It's one strand wrapped around itself. And then if you zoom in on the sides of one of these strands to see what they're made of, you again find some of those bow tie structures again. There's several of them. There's one there. And then spiderweb structures and the spirals, single spirals now. Zooming in on one of the bow ties, it's the same as before, except now it's a single spiral. The bow ties before were double spirals. So it inherits the properties of the parent that it grows off of. And quite lovely. Who could have imagined that such beauty would be built into numbers? Beauty that occasionally PowerPoint can't handle. And this is an Alienware too, so it just goes to show you. So there's one of these bow ties in all of its glory. And again, it goes from 2 central hubs, and you can see there's 4 in the middle, and then 8 and 16 and 32. Each one doubles the previous one. So we go into the center there. And isn't that lovely? And just, I mean, it'd be one thing if I just said, oh, here's some pretty stuff that a computer generated. But this isn't something that a computer generated. It's something that a computer revealed. Because computers are not responsible for numbers. They merely use numbers. God's responsible for numbers. And in principle, again, you could plot the shape by hand. You could manually run the numbers through that. I've shown you how to do it. We did the first 2 manually. You could run the numbers through that and plot the shape. And this is what you'd get. The computer just does it very quickly. But my point is that the computer didn't make it. People didn't make it. This shape exists in the mind of God. And there's no naturalistic explanation for this. There really isn't. So all of that, the points that belong to that formula, for which z is bound under z squared plus c. Isn't that amazing? So then it made me think, well, that's just one formula, right? I mean, you could spend your life studying that shape. It's infinite. It goes on forever. But I want to explore other shapes. What happens if you change the formula? What happens if you try z cubed plus c? Well, it turns out you get a different shape. And now I have another infinite shape that I could spend my entire lifetime exploring. And it's similar, but it's a little bit different. Everything kind of gets doubled. The basic shape that you have here is called a nephroid. And it's you notice everything's gone up by 1. The circles have become cardioids, right? So circles have no cusps. Cardioids have 1 cusp there. The main shape itself, which used to be a cardioid, is now a nephroid. A cardioid has 1 cusp, a nephroid has 2 there and there. So it's got another one now. And a nephroid is what happens when you take a circle that's half the size of the original and you roll it around, keeping your pencil affixed to a point on the smaller circle. That's the shape that you get. And you can see that. That's exactly what it is. It's a perfect nephroid. Why? I have no idea. That's what it is. That's what it is. And in fact, what we can do is we can incrementally, I even tried intermediate powers. Like what happens if you do z to the 2.1, 2.2, 2.3, and you can see how one shape kind of morphs into the other. Let's see. So that was kind of a fun little experiment. So you can see how the Mandelbrot becomes what we call a multibrot, because it's a multiple of the Mandelbrot. So there's the Mandelbrot, and then there's the first multibrot, z cubed plus c. And you can see how everything kind of gets doubled. Some things get quadrupled. Like the baby Mandelbrot there, it gets split into 2, and then eventually it gets split into 4. So there's 1, 2, 3, 4. So there's now 4 baby versions of the original. So some things get quadrupled, but most things are doubled. And so I wondered, okay, well, what happens when we zoom in on this? Is it also a fractal? Does it have a valley of elephants? That's the one section that doesn't change very much, right? Because the Mandelbrot set had this valley of elephants. Does the nephroid have a valley of elephants? Well, let's check it out. Let's zoom in. Thanks to the power of computers, we can do that. So we zoom in there and we find, lo and behold, you see elephants. How about that? Elephant after elephant. Kind of interesting. But remember, before we had 1 elephant growing on each circle. But the circles have split into cardioids, and now we have 2 elephants on each cardioid. See, 1, 2, 1, 2. So before we had an infinite number of elephants, and now we have twice that many. That's pretty neat. Simmer on that for a little while. Infinity is such a weird concept, but it's real. Yeah. So we'll zoom in on that. Zoom in on one of these curly trunks, and again, it's a single spiral like before. Think we'll find bow ties again? We found those last time. Well, we zoom in and we find that this time, instead of having bow ties, we have tri-ties. See, instead of 2 loops, it's 3. Isn't that interesting? So it went up by, well, it kind of makes sense. We went from z squared to z cubed, and so they go from 2 to 3. And when we zoom in here on the middle, it goes from 3 to 1, 2, 3, 4, 5, 6, 7, 8, 9 to 27. It's all the powers of 3. And so you get a different shape. When you zoom in on the baby version, lo and behold, you have another baby multibrot. So it is also a fractal. It repeats itself infinitely, and it gets more and more beautiful the more you zoom in. That's interesting. That, I think, is an aspect of God that He's built into His creation, or at least in the world of mathematics. The more you zoom in on it, the prettier it gets. So that's what happens when you have z cubed. I'm just having fun playing with these different sets, wondering, what do you get? What do you get when you try z cubed? What do you get when you try z to the 4th? Well, you get that. Okay. And it goes on forever too. You can zoom in on it. It's got baby versions of it. And now I'm starting to see a pattern, right? Because the first multibrot, the z cubed plus c, has a 2-fold structure, right? This is a mirror image of that, right? Two kind of main lobes. Z to the 4th has 3 main lobes. And so naturally z to the 5th has 4. It's always 1 less than the power. And z to the 6th has 5. And so it occurred to me, if I did z to the 7th, I could get snowflakes. And you sure do. You get snowflakes. And if you zoom in on them, do you get baby snowflakes? You sure do. Of incredible beauty. Isn't that awesome? Isn't that awesome? And then I started playing with negative powers. What happens if you go z to the negative 2? You get that. That's interesting. And remember, black is points that do belong to the set. And so now most of the universe belongs, right? Because we have a negative power, so it kind of flips it inside out. So most of the universe now belongs to the set. And these are points that don't, these points in here. And you get these little pebble-like structures. And I zoomed in on those. You think it's going to be fractal? Is it going to repeat infinitely? Let's have a look here. So you have these wonderful little pebble structures. And we'll zoom in on that and see if it kind of continues infinitely. Stunningly beautiful, at least I think it is. Zoom in on that. And you think it's going to stop. We're going to get down to nothing. And it just doesn't. It just keeps going. So it's also a fractal that continues infinitely to repeat the same basic pattern. Isn't that astonishing? Little window into the mind of God. Little window into the mind of God. So that's z to the negative 2. I tried z to the negative 3. You get that. Z to the negative 4. Z to the negative 5. There's another way to make snowflake. Z to the negative 5. You have an inside-out snowflake. So and it's just fun to explore these shapes. But let's get down to business now. What does all this mean? Are we just looking at pretty shapes? What causes the beauty in fractals? What causes the complexity in fractals? The fact that you can zoom in forever. They're infinite. They repeat infinitely. Well, let's start with the first. What causes the beauty in fractals? What are some possibilities? Well, some people have said, well, Lyle, you picked pretty colors. It's the man-made color scheme. And I told you, the colors are arbitrary. I could pick whatever colors I want. I picked ones that I think look nice. There's some programs that people have written that don't pick very nice colors, and shame on them, right? But I don't think it's the colors that create the beauty. I think they enhance it. But the fact is, the shape itself is beautiful, even in grayscale, with no color at all. The shape is beautiful. There's something about this shape that strikes us, and we say, yes, that appeals to my sense of beauty. So I think the color enhances it the way salt will bring out the flavor of a food, but it doesn't create the beauty. The beauty's already there. The man-made color scheme just kind of brings it out a little bit. Did the computer create the beauty? Now, you might think that. You might think, well, I saw your computer plot that there, Lyle. But the fact is, that shape has been built into numbers since creation. The computer just revealed it quickly. And again, you could plot this by hand. You could plot it by hand. You could sit down and run the numbers through that formula. I showed you how to do it. It's tedious, but you could do it. And you could plot each of those points by hand, and you find the same shapes there. The computer did not create it. The computer merely revealed it quickly. Did people make this? Well, in the sense that we decided what formula to check, but once we picked the formula, the shape's determined. You have to run the numbers through that, and we didn't create numbers. It's not like any human being sat down and said, I'm going to make this incredibly awesome shape with a cardioid here and some circles, an infinite number of circles growing off of it, and an infinite number. We can't create infinite things. No human being made this. Not at all. Human beings were surprised when the shape was discovered in the 1980s, when computers were finally fast enough to be able to plot these things in a relatively reasonable amount of time. You wouldn't be surprised by something you yourself made, right? You wouldn't make something and you say, well, how about that? I had no idea it would be like that. That would be rather silly. No, people didn't make it. Somehow it's built into math. The beauty is somehow built into numbers, revealed when we run through that little formula. So what causes the complexity in fractals? The fact that they repeat infinitely and have all these interesting shapes. Again, I'm going to ask, did the computer create it? No, the computer didn't create it. The computer revealed it, and it revealed it quickly. The computer didn't create the shape any more than microscopes create bacteria. Microscopes allow us to see bacteria. The computer allowed us to see a shape that had been hidden in numbers since creation. Did human beings create it? Well, again, we were astonished. We were surprised by what we found. We didn't create this. We did pick the formula, but that's it. The shape then is determined by the laws of mathematics. It's not something that we created. Did the formula create it? Well, again, the formula revealed it, but we found that when you change the formula, you still get incredible beauty. Somehow the complexity is built into math itself. It's not something that human beings made. So what is math? Well, math is the study of the relationship between numbers. That's just the dictionary definition of mathematics. And of course, being an amateur philosopher, I'm going to ask then, what are numbers, right? Well, come on, Lyle, we know what numbers are. Have you ever tried to define what numbers are? It's some of these things that we take for granted, like consciousness, are very hard to define without referencing something that basically means the same thing. Consciousness, self-awareness. Well, but what does it tell me, right? What are numbers? I consulted a number of dictionaries. The best definition I could find, and I think it's a good one, is that numbers are a concept of quantity. Numbers are a concept of quantity. Yeah, that works. So conceptual, something that exists in the mind. So you can have 3 apples. Now the apples are not the number. It's the 3 that's the number, right? And that number is conceptual. You could remove the apples and you could still have the conception of 3-ness. So what do 3 apples have in common with 3 oranges? I mean, their atoms are totally different. Their properties are different. What they have in common is 3-ness. 3-ness. It's a concept, isn't it? So numbers are concepts. They are abstract in nature, not physical. They exist in the mind. You cannot stub your toe on a number. You could stub your toe on a number of things. You could stub your toe on 3, rocks, but you can't stub your toe on 3. Because it's not physical. It exists, but it's not physical. You say, well, I don't know. I think that's the number 3 right there. It's physical. It's on the screen. But is that really the number 3? Because if it is, then I just destroyed the number 3. And poor children will now have to count 1, 2, 4, and so on. Well, you say, well, that's not really the number 3, is it? That's a representation of the number 3. And I can remove the representation, and 3-ness still exists. Numerals are not numbers. They're representations of numbers. And we can represent it differently. We could represent it with 3 capital I's. That's how the Romans would represent the number 3. It's still the same number, isn't it? It just has a different representation. So human beings created the notation that we use for numbers, but we didn't create numbers. No, we didn't create numbers. They already existed. Laws of math, which govern the relationship between numbers, are conceptual. They exist in the mind. So here's the question that I'm going to ask. Where do laws of math come from? The fact that 2 plus 2 equals 4. See, well, that's obvious. Everybody knows that. Yeah, everybody knows that, but where does it come from? Did laws of math evolve? Now, see, in the physical universe, when we have things like biological organisms, and they have all this design in them, they're well constructed, they work well. And the way evolutionists like to explain that, the way secularists like to explain that is evolution, right? They say, well, they weren't originally that way. Originally, they were very simple, but then they became more and more complex over time. Is that going to work? Of course, that doesn't actually work. But is that going to work with math? Is it like 2 plus 2 used to equal 7, but now it evolved, and now it equals 4? No, laws of math don't evolve, right? Because numbers don't evolve. It's not like 7 used to be 3, but then it evolved. Or that 3 and 7 have a common ancestor. No, it doesn't even make any sense. Numbers are what they are. They do not change. The relationships between numbers do not change. 2 plus 2 has always equaled 4, hasn't it? Were they created by people? Some people say that. You think human beings came around and decided, you know what, I think 2 plus 2 should equal, I think it should equal 4. And we all kind of agreed on that, shook hands, and that it just became that way? Ridiculous. Laws of math were not created by people. They were discovered by people. If they were created by people, we could have created them differently. We could have said 2 plus 2 equals 3, and we all agree to that, and that would work. But can you imagine trying that Go to a bank and say, I've decided that here's what my account should be. That's not going to work out well for you, is it? Or an architect who decides that laws of math are arbitrary, they can be whatever he wants. I would not walk into that building. They're not created by people because in fact, they existed before people. The relationship between a planet's period and its orbit around the sun, which Johannes Kepler discovered, that's a mathematical relationship. P squared equals A cubed. People discovered that. They didn't create it. Planets orbited perfectly well before people were around, right? And they obeyed that law for 2 days. Because they're made on day 4, humans are made on day 6, yes? Do laws of math come from the universe? Some people say that. That's just, laws of math describe the way the universe is. Well, it is interesting that we can use laws of mathematics to describe various aspects of the universe, but they don't come from the universe. Because the universe is changing. It's expanding, stars explode. If laws of math merely reflected the way the universe is, then they would be changing, wouldn't they? Because the universe is changing. You don't want to make laws of math contingent upon the universe because then you would make them contingent upon something that's changing. And frankly, you'd expect them to be different in different places because the universe is hot in some places and it's cold in other places. And so you'd expect laws of mathematics would be different. And if they were just merely reflections of the way the universe is, because the universe is different in different places. So they didn't come from the universe. I want to suggest to you that laws of mathematics stem from the mind of God. God is the person who determines mathematical truths. God's mind is not like our mind. There is a similarity because we're made in God's image. We can think, we can be rational. But our minds discover truth, whereas God's mind determines truth. You ever thought about that? What God thinks is what is true. Something is true if it corresponds to the mind of God. And so God has determined what the relationship between numbers is, and that's the relationship between numbers. And we as creatures discover that relationship systematically over time. We pass it on to our children and so on, and knowledge builds. But it makes sense that laws of mathematics stem from the mind of God when we consider their properties. Laws of mathematics are conceptual, meaning they exist in a mind. Well, that makes sense because God thinks. Laws of mathematics are universal, meaning they're the same everywhere. They're invariant, meaning they don't change with time. And they're exceptionless. It's not like 2 + 2 = 4 most of the time, but every now and then it's 17. And these things make sense in light of the fact that laws of mathematics stem from the mind of God. Of course, laws of mathematics would be conceptual because all thoughts are conceptual. And so when God thinks something, it's going to be conceptual. Of course, laws of mathematics will be universal. They'll be the same everywhere. Why? Because God is omnipresent. God's thinking determines truth everywhere in the universe, not just on the earth. And so we expect laws of mathematics will work everywhere the same way they do on earth. Laws of mathematics are invariant. They don't change with time because God doesn't change with time, and therefore his thinking does not change with time. Isn't that right? I, the Lord, do not change, therefore you sons of Jacob are not consumed. God's beyond time. He made time. And so naturally his thinking isn't going to change. Therefore, you can trust that 2 + 2 will equal 4 tomorrow. It will. Count on it because God does not change, because God is faithful. And they're exceptionless. There are no exceptions to laws of mathematics because God is sovereign over all truth. All truth claims are determined by him. But the naturalist has a dilemma. The person who says, there's no God, or if there is, he's within nature. He's certainly not the biblical God. He's got a dilemma. Because on the one hand, laws of mathematics are conceptual. They exist in a mind. But the naturalist doesn't have a mind before people. Problem, right? Laws of math require a mind because they're conceptual and concepts require a mind. And yet laws of math existed before people. So they're not the result of human minds. But if nature's all that there is, according to the secularists, there was a point where the universe had no minds, but it still had laws of mathematics. But you can't have laws of mathematics without a mind because they're conceptual. Problem. It's an inconsistency in secular thinking. But it makes sense in the Christian worldview where God determines truth. There are other types of fractals. There are physical fractals, or at least things that are approximate fractals that exist in nature. The fractals we've looked at so far, the Mandelbrot set and the variations of it, the multibrots, those you can't touch those. They're not made of atoms. They're made of math. They're made of numbers. They're maps of numbers. But there are things in the physical universe that, when you zoom in on them, they repeat either exactly or approximately up to a certain point. They don't go on forever because eventually you get down to atoms and they're not fractal anymore. But there are things that are approximate fractals. Let me give you an example of fractals in the physical world. I'll give you several examples. First of all, snowflakes. Snowflakes are fractal. They have that six-fold symmetry. You zoom in on them. You still have six-fold symmetry. You zoom in on them, six-fold symmetry, and so on. So these little gems from heaven that the Lord sends us, and we go and scrape them off our car, and ugh. But they're actually lovely. They're beautiful. Little fractals. Isn't that interesting? That stuff that grows on your windows is fractal. You see the way it branches, and then it branches into branches and branches into branches and branches, and so on. It continues down up to a certain point, and then it stops. So it's an approximate fractal. Certain ferns are fractal because you have the main leaf, and then it branches off into leaflets, who branch off into smaller leaflets, and so on, up to a certain point. So each section resembles the original in a sense. I even found fractal broccoli, so I guess broccoli is good for something after all. There you go. See that? It's a cone made up of cones, which are made up of cones, which are made up of cones. Isn't that fascinating? And so it's just a shame it's so disgustingly its taste. But anyway, coastlines. Coastlines are fractal because the way they branch, and then they branch into branches and so on. Mountain chains are fractal when you look at them from above because of the way the mountains branch and branch into branches and so on. Clouds are fractal. Am I looking at the entire sky, or am I zoomed in on a very small section of a cloud? It's hard to know. Because you zoom in on a cloud, it looks kind of like a cloud, doesn't it? It kind of repeats that pattern. The way lightning branches is fractal because you have the main bolt and it branches into branches and they branch into smaller branches and so on. So the way lightning branches is fractal and quite beautiful actually. And it's interesting too to watch it in slow motion where you can actually see the branching happening as the lightning strikes until the leader connects, and then most of the current goes down the leader. But isn't that fascinating? So there are lots of things in the physical world that are approximate fractals. So then I'm going to ask this question. Why do fractals occur both in math, which is not made of atoms, and the physical world, which is made of atoms? Why do they occur in math, which is conceptual, and the physical world, which is not conceptual, right? I mean, after all, this shape, that's a mathematical plot. That's one of the multiplots. We saw that earlier. That's what happens when you plot all those points that are bound under z to the 5th or z to the 7th plus c. That doesn't exist physically, but that does. Yeah, you can see that in the winter. That shape is that's part of the Mandelbrot set. It's one of those branches in the Mandelbrot set. You can't touch that. But that you could, although you shouldn't. That's physical. Yeah. You say, well, that's a plant. No, it's not. That's a mathematical graph called a Barnsley fern. It's a mathematical graph where each leaflet is the entire shape. Let me show you. Watch the entire shape. It becomes its own leaflet. See that? That's just cool, isn't it? Let's do that again. Yeah. So the entire shape is each leaflet. That's a mathematical graph. On the other hand, that is physical. That only exists in a mind. That exists physically. You can touch it. That shape is a mathematical graph, but that grows on your windows. One is abstract, the other is physical. This shape is a mathematical graph, cones on cones. It does not exist physically, whereas this, unfortunately, does. This shape is a mathematical graph, part of the Mandelbrot set. You can't see it in a telescope because it's not physical. You have to plot it using a computer because it exists only in the mind of God. And yet, that shape you can see in a telescope, and I have many times. The Whirlpool Galaxy just off the tail of the Big Dipper. So, why is it that fractals occur both in math, which is conceptual, and the physical world, which is not conceptual, is in fact made of atoms? Now, one answer, and I think it's a reasonable one, but it falls short of the complete answer, is that, well, the physical universe obeys mathematical laws, and that is true. We can write down equations to explain how the universe behaves. So it stands to reason if fractals can occur in math, they can also occur in the physical world, which obeys math. Okay, but then of course I'm going to have to ask, why does the physical world obey math? That's what I want to know. And we take that for granted, that you can write down math formulae that describe the physical universe. Like E equals mc squared. Have you heard of that one before? Yeah. That's one of the ones that Einstein discovered. And it's true, and it applies to the physical universe, or F equals ma, or whatever, these various formula. But how is that? How is it that these formula that are conceptual, that exist in the mind, somehow apply to the physical universe, which does not exist in the mind? What's the connection between these two? Well, in the Christian worldview, I can make sense of that, because mathematics is a reflection of God's thoughts And God's thoughts are what controls the physical universe. In fact, created the universe and upholds it. So it stands to reason that since God thinks mathematically, and since the universe is upheld by the mind of God, that the universe will obey math. It makes sense, doesn't it? In the Christian worldview, it makes sense. The universe obeys math because the universe obeys God, and God thinks mathematically. So I as a Christian, can explain, at least in general principles, why the physical universe obeys mathematical laws, and therefore why physical fractals can exist and why they reflect mathematical fractals. But I want to suggest that the secular worldview cannot cogently answer that. They can't explain the properties of laws of mathematics, how we could possibly know that mathematics has these properties, the fact that laws of math are universal, they're the same everywhere, the fact that they don't change with time. How do you know that? How do you know that math is the same in the Andromeda Galaxy? It's not like you've been there. And yet everybody assumes that because everybody knows in their heart of hearts God, you see. Why it is that the physical universe is compelled to obey math. We take it for granted. We take it for granted. Of course the universe obeys mathematical laws. We've been discovering them for thousands of years, right? But secularists cannot explain it. They can't. Unless you think I'm making that up, I want to show you a paper written by Dr. Eugene Wigner, who is a brilliant physicist. He is a Nobel Prize winner. This is no slouch. He's brilliant. And he wrote an article years back called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. You see, he's not a Christian, as far as I can tell. He's not a Christian, and he's trying to explain from a naturalistic perspective, why is it that the universe obeys, the physical universe obeys mathematical laws, which are conceptual? And the paper is a wonderful read because he doesn't really have an answer to it. He comes across and says, it is difficult to avoid the impression that a miracle confronts us here, or the two miracles of the existence of laws of nature and of the human mind's capacity to divine them. He says it's amazing enough that there are laws of nature, because without a lawgiver, why would you have laws, right? That's amazing enough that there are these mathematical formula that the universe obeys. And it's even more amazing that human beings can figure it out. How is that? He can't make sense of it in his worldview, you see. What is the conclusion of this? And I'm not making fun of him. I respect this guy. I respect his honesty. I respect his brilliance. But what is his conclusion? From a secular perspective, how does he explain the unreasonable effectiveness of mathematics in the natural sciences? Here's the answer. This is the conclusion of his article. The miracle of the appropriateness of the language of mathematics for the formulation of laws of physics is a wonderful gift which we neither understand nor deserve. Isn't that interesting? He is utterly perplexed from a non-Christian perspective as to why the physical universe obeys math. And I dare say there is no solution in the secular worldview. It's only the Christian worldview where we have a God who is transcendent, who is responsible for numbers, and is also responsible for upholding the physical universe. You see, that's the connection between math and the physical universe. Both of them are aspects of the way God thinks. The mathematics is the way God thinks about numbers. The physical universe is something God spoke into existence and upholds by the word of his power. That's why they go together. Why can we discover laws of mathematics and laws of nature? Because we're made in the image of God, and God has given us that gift of rationality. And we're able to discover these things and reliable senses whereby we can probe the universe. You see? So I can make sense of the effectiveness of mathematics in the natural sciences. And in fact, in the last chapter of my book on the physics of Einstein, I wrote a little section called The Reasonable Effectiveness of Mathematics in the Natural Sciences. Because you see, I can make sense of why science works and why it obeys math. I can make sense of that as a Christian. So we've seen that there's beauty of infinite complexity. Yes, fractals are infinite, the mathematical ones anyway. The Mandelbrot said it'll go on forever. It's infinite. It's built into numbers, revealed by that little formula. Numbers are abstract conceptions of quantity, which means they require a mind because concepts require a mind. You can't have numbers without a mind. But we have a mind that's beyond human minds, the mind of God. That's why you can have mathematics can go into things like infinity, and that's because God's mind is infinite. We have trouble with that, but God doesn't. Numbers are a reflection of the way God thinks. They're the way God thinks about mathematics is the way God thinks about numbers. The relationship between numbers is determined by the mind of God and discovered, in some cases, by the mind of man. The secular worldview cannot account for the existence of numbers, why it is that you can have these abstract conceptions before human beings existed, or their properties, why it is that 2 + 2 = 4. You can't even explain that in a secular worldview. We know it's true, but you can't explain it. You can't account for it. Their properties, the fact that mathematical laws don't change over time or space. They're the same yesterday, today, and forever, because Jesus is the same yesterday, today, and forever. And his mind is responsible for mathematical truths. And also, they can't explain how we could possibly know any of these things. Granted, maybe laws of math are universal, but how do you know that? I know that as a Christian because it's by revelation. God has told me, and He's infinite, so He knows everything. So if He tells me that He upholds all creation, then I can trust that He does. Numbers existed before people, yet they're conceptions, meaning they require a mind. The naturalist has a problem because he doesn't have minds before people, but he's got numbers before people. But numbers require a mind. That's a problem. Laws of mathematics are universal and very abstract entities, which makes sense given the fact that God is omnipresent, doesn't change with time, and His thinking is abstract, as all thinking is. The physical world also contains fractals, at least approximate fractals, and yet the secular worldview cannot account for why the physical universe obeys mathematics. We've seen even the most brilliant physicists have not been able to figure that out. And there's been no improvement since Wigner. The universe is controlled by the mind of God. I can make sense of this from a Christian perspective. So in terms of resources, again, I want to push the ultimate proof of creation as well as the DVD. And nuclear strength apologetics would be a follow-up to these kinds of presentations as well. If you want a book on this topic, I'm working on it. And it's going to be awesome. It's going to be beautiful. And the DVD on it will be finished even before that. We might have the DVD out next month even on the fractal presentation. So, because it's worth sharing. It's just neat. And again, understanding Genesis, how to defend the 6 days of creation and why it really does matter, as long as the DVD on that topic. And again, don't forget, we have lots of astronomy materials as well. That's my specialty topic, as well as Keeping Faith in an Age of Reason, answering 400 alleged Bible contradictions, the physics of Einstein. It's exactly what you think it is. Equals MC squared, that kind of stuff. Black holes. I love black holes. They're just fascinating. And there's a whole section in that book on that topic. And then I think we're out of dinosaurs. But you can back order stuff if we run out. And don't forget to sign up for our free monthly newsletter. And I don't make a big deal out of funding because I want to be as generous as possible. But if you can partner with us, we'd appreciate that. We do have on the website you can contribute some monthly amount. It's up to you what you want to contribute. We have several different levels, but we are funded by donations, so we'd appreciate that if you can do that. And if not, then enjoy it for free. I really had students in mind when I created this ministry, and students don't have any money, so so I made it free for that reason. So I want to thank you very much, and we'll be back in 10 minutes for Q&A. Thank you very much.